Testing, can you hear me? Testing, can you hear me? Okay, I'm testing one last time. And this video is now public. Let me just change to full screen. Okay, so I'm going to be studying sequences again. I will just start studying from where I last left off. So I studied about describing sequences, rate of growth. Rate of growth, they talked about arithmetic and geometric sequences. And this stream, I'm going to study about polynomial sequences. I think I will do these two chapters this stream. A standard 80 by 8 chessboard contains 64 squares. Actually, this is just the number of unit squares. How many squares of all sizes are there on a chessboard? Start with smaller boards, 1 by 1, 2 by 2, 3 by 3. Find a formula for the total number of squares in an n by n board. Isn't it just n times n? Oh, they're saying actually this is just the number of unit squares. How many squares of all sizes are there on a chessboard? So on a 1 by 1 chessboard, you just have one. On a 2 by 2 chessboard, you have 1, 2, 3, 4, and then 5. They're only talking about squares, right? How many squares of all sizes? Okay. On a 3 by 3, I think this would be easier. Or maybe not. So one unit square, there would be 9 of these. 2 unit square, there would be 4 of these. 1, 2, 3, 4. And then you have the big one. So it's 1, 4 plus 1, 5, 9 plus 4 plus 1, 14. Is there a pattern though? Okay, let's try 4 by 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there is 16 of the small ones. 1. Let's try 2 by 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of these ones. 4 of these. 4 of, and then 1 big one. So 9, 4, 1. 16 plus 9 plus 4 plus 1. 16 plus 9 plus 4 plus 1 is 30. Nine, 4, 1. 14, 4, 1. I think I'm seeing a pattern here. If I do it 5 times, 1, yep, this, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 5. 25 of these. And then the 4 by 4 one we have, sorry, wait, 2 by 2 one. 1, 2, 3, 4, 16 of those. And then the 3 by 3 one, we have 4 of those. No, wait. We have 9 of these ones. 4 of these ones, and then 1 big one. So plus 16 plus 25 is 55. So 1, 2 square, 9 square, 16 square, 5 square. So for n by n boards, number of squares in n by n board, n by n board is equal to n square plus, actually wait, n square plus s of n minus 1. I think this is the question. So if it's n is 2, 2 square plus 1 is 5. N is 3, 3 square plus 5 is 14. This is the equation. I'm deriving this because of a pattern, but I want to know what the proof is for all of the things. Um, we have seen that arithmetic sequences grow at a constant rate, so their closed formulas are linear functions. What about sequences that grow faster? What if their rate of change is itself growing at a constant rate? In section 4.2, we claim that the triangular numbers, the sum of the first n positive integers, have closed formula. Tn is this. So this sequence, whose sequence of differences is arithmetic, is a degree 2 polynomial, a quadratic function. Our goal in this section is to explore this phenomenon. We will verify that this really is the closed formula for the triangular numbers, extend it to other sequences with arithmetic differences, and then explore sequences that grow at even faster rates. While wandering the halls of the math department, you find yourself staring at the captivating artwork shown below. How many dots are there in the figure? The dots form a uh, 1, 2, 3, 4, 5, 6, 6, 6, and total of 36 dots. You can also compute the total number of dots by summing each hook region from the smallest to largest. 1, 3, 1, 2, 3, 4, 5, 1, 3, 5, 1, 2, 3, 4, 1, 2, 3, 7, 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 9, 1, 2, 3, 4, 5, 6, 6 plus 5 is 11. Adding plus 2 every time, right? Okay, I think that makes sense. One dot here, one dot here, and then two extra on the edges, like at the two ends. Imagine this is a hallway, and at the end of the hallway there are two dots. Now these three, put them over here, and then add extra two dots at the end. These five, put them up here, and then add extra two dots at the end. And this pattern would repeat. So it's plus 2, right? Yet another way to calculate the total number of dots is to group the terms of the sum. 1 plus 11, 12, 12, 12. Since there are three pairs of sum, the total is 36. Why are we doing first and last? We generalize the diagram so it has n hooks. How many dots will be in the largest hook? So n hooks. So hooks 2, 3, 4, and then dots 1, 5, sorry, 3, 5, 9. Let's do this is n is equal to 1 dots a n, and then 1 plus t. This is the sequence. How many dots will there be in the largest hook? 1 plus 2 and minus 2. Let's just check if this is correct. If there are 6 hooks, 1, 2, 3, 4, 5. What is a hook? I don't understand. This hook is a region, right? If there are 6 hook, in the largest hook you will have, so we plug in 6 here. 6 times 2 minus 1 is 11. That makes sense. 2 and minus 1. How many in the second largest? Minus 4. 2 and minus 3. What will the sum of the largest and smallest and largest hooks be? So this plus this, 4 and minus 4. Wait. Sum of the smallest and largest hook. Smallest has a 1. Would be 2n, right? And then same thing here. It's an arithmetic sequence, so first and last should be same. If we continue adding pairs of hooks, how many pairs will we have? So n by 2 pairs. N by 2. Dots will be n square. Summing arithmetic sequences, reverse and add. Oh, this is what I did last stream. 1 plus 2 plus 3 plus n, and then n plus n minus 1, and then we get this, and then we get this. Find a closed formula. We have plus 4 plus 4. N, A, N, 1, 2, 3. Hold on, we already have a formula, right? Example 4.3.2. 6, 10, 14, and then this. So the sum sum is n over 2, first and last, but we don't know n. We don't know what this is. They're asking us to find the formula. So 4n minus 2. I can take the 4 out. Why don't they take the 4 out from here? Take the 4 out, and then we have 2 times all of this. 2 times n minus 1 and a plus 1. Wait, I don't understand how they got this formula. We did n minus 1. They're getting 4n plus 4. Yeah, and then that n minus, we have this. Why are they saying n minus 1? Shouldn't it be n times? Okay, I don't understand what they're doing here. This is n terms in total, right? Or maybe not. If we plug in 4n minus 2, if we plug in 1, we get 2. If we plug in 2, we get 6. Oh, it's starting from 2. It's starting from n is equal to 2. So there are not n, there are there. The total is not n, the total is n minus 1. So it's n minus. Higher degree polynomial, since we know how to compute the sum of the first n terms of the arithmetic sequences, we can compute the closed formulas for sequences that have an arithmetic sequence for differences between terms. But what if we consider a sequence that is the sum of the first n terms of a sequence that is itself the sum of an arithmetic sequence? How many squares are there on a chessboard? Chessboard consists of 64 squares, but we also want to consider squares of longer side length. Even though we are only considering an 8 by 8 board, there is already a lot to count. So instead, let us build a sequence. The first term will be the number of squares on a 1 by 1 board. Second term will be the number of squares on a 2 by 2 board, and so on. The sequence is 1, 5, 14, 30, 55. It is not arithmetic, and the difference is 4, 9, 16, 25. Not a huge way to count, not a huge surprise. One way to count the number of squares in a 4 by 4 chessboard is to notice that there is 16 squares, side length 1, 9 with side length 2, 4 with side length 3, and 1 with side length 4. So the original sequence is just a sum of squares. Notice that this sequence of differences is not arithmetic, since its sequence of differences is not constant. Wait, going back to the top. For a 5 by 5 board, there are 9 4 by 4 boards, right? Sorry, there are 4 4 by 4 boards. I think another way to express this is so 1 counting the large square plus plus n minus 1. No, wait, plus 4. So in this board, in a 4 by 4 board, there are 4 ways to count 3 by 3. There are yeah. So there are 4 ways to count 3 by 3. So 1, 2, 3, 4. For a 5 by 5 board, there are 4 ways to count 4 by 4 squares. So 1, 2, 3, 4. Similarly, for a 2 by 2 square, there are 4 ways to count. There are 4, for a 3 by 3 square, there are 4 2 by 2 squares. So 1, 2, 3, 4. So wait. How do I? Never mind. Chessboard question. For S and 1 to count the big square, and then 4 to count the smaller square, right? 4 to count the smaller square, like which is one size smaller. But within the smaller square, there are S n minus 1 squares inside. So like for a 4 by 4 chessboard, there are 30 squares. So that means within this 4 by 4 square, there are 30 squares. Within this 4 by 4 square, there are 30 squares, 30 squares, 30 squares. So 1 for the big square, 4 smaller squares, and for each of those 4 squares, we have to For each of those smaller squares, there is s n minus 1 squares, right? There's one new formula. But if this is true, then we have n squared plus n minus 1. If that's right, so wait, if n is 5, if n is 5, n is 5, then S4 is 4 square minus 1 divided by 3. F4. So what is 5? N is 5. And then we have 8. It should be 30. This answer is not correct. Something is wrong here. If I plug in 5 here, 1 plus 4 times 30. 4 times 30. Something is not wrong. Something is wrong here. Maybe it's addition. One plus 4 plus 30. 1 plus 4 plus 30. Nope. Um, there are 30 squares here. The 34 by 4 squares. Those 34 by 4 squares will appear 4 times. Oh, now I understand what I'm doing wrong. I think I'm counting the singular squares twice. I see, yeah, that's right. Yeah, I understand. This is wrong because I'm counting the smaller squares multiple times. I thought I had something. 25, 16, 9, 4, 1. I don't know. So for differences, we get 4, 9, 16, 25. Not a huge surprise. So the original sequence is just a sum of squares. Now, this sequence of differences is not arithmetic since it's a sequence of differences. Since its sequence of differences is not constant. In fact, the sequence of second differences is 597, which is an arithmetic sequence. Notice that our original sequence had third differences constant. We will call such a sequence delta cube constant. The sequence 1, 4, 9, 16 has a second differences constant, so it will be delta square. Which of the following sequences are delta k constant for some value k? This was useless. Example 4.3.4. 2, 3. I'll just take a screenshot. So for number 1, 3 minus 2 is 1. 7 minus 3 is 4. 14 minus 7, 7. 24 minus 14 is 10. Then 37 minus 24 is 13, right? 4 minus 1 is 3. 7 minus 4 is 3. 10 minus 7 is 3. 13 minus 10 is 3. 8 minus 1 is 7. 1964. Twenty-seven 64. But this is wrong. I think it's 37. 7 plus 7 is 14. Just use a calculator. 64 minus 27. 125 minus 64. 61. 19 minus 7 is 2. 37 minus 19. 18. 61 minus 37. 24. 16. 24 minus 18. 6. So this. Yeah, I don't think this one is any sequence because it's going negative here. It's going negative here, but the sum are increasing. So I don't think this one is correct. 1, 2, 4, it's 16, 32, 64. Yeah. That would be 3. 4 minus 2, 8 minus 4. 1, 2. 8 minus 4 is 4. 16 minus 8 is 8. 32 minus 16 is 16. So this is not either. It gives the same sequence back. These are perfect cube. The sequence of the first differences is 7. Sequence of the second differences is this. Wait, what? 7, 9. Oh my gosh. minus this 12. This is 6. 216 minus 125. 91. Minus 24. Is that correct? This minus this minus this. This minus this. 61 minus 37. It's 24. 125 minus 64. I think this is supposed to go. Yeah. And then 91 minus 61. It's 30. Yeah, that makes sense. The delta zero constant sequences are themselves constant, so a closed formula for them is easy to compute. Delta 1 constant sequences are arithmetic. Every delta 2 constant sequence is the sum of an arithmetic sequence, so we can find formulas for these as well. But notice that the format of the closed formula for a delta 2 constant sequence is always quadratic. For example, the square numbers of delta 2 constant with closed formula a(n) is equal to n squared. The triangular numbers have a closed formula a(n) is equal to n times n minus 1 over 2, which when multiplied out gives out an n squared term as well. The way is that every time we increase the complexity of a sequence, that is, increase the number of differences before we get constants, we also increase the degree of the polynomial used for the closed formula. Closed formula for a sequence will be a degree k polynomial if and only if the sequence is delta k constant. Find a formula for 3, 7, 14, 24. 3, 7, 14, 24. The delta 2 constant. Wait, if we have a 1 actually and a1 plus d1. So the first term is a, and then a plus d1, a plus d2, a plus d3. And d1 is like k plus k. A plus d n minus 1, a plus d. This is n minus 1. This is n minus 2. Wait, something isn't right. I did plus t1. Hold on, this is wrong. Plus k plus k. So here we have the first level difference, the second level difference, the third level difference. Plus k is okay. So we have a plus t, a plus kd. And then if we do plus k, no, wait. I need to space these out a bit. So a plus t, which is this, and then the next term plus t plus d plus k. This should form an arithmetic sequence. Plus d plus 2k. A plus d k k. So the pattern it's following is a plus d. No, I think there is something wrong here. This should be like this. A plus d and then a plus 2d plus k. And then 3d plus 2k. So a plus n is equal to 1, n is equal to 2, n is equal to 3. 1, 2, n is 1, n is 2. N is 1, n is 2, n is 3, n is 4. Okay, that makes sense. Plus let's see. Plus k plus d plus 3k a plus 4d plus down a minute. D plus k d plus this becomes 3. Then this becomes 6k. There is an arithmetic sequence here, right? This over here, the middle one, it follows this sequence d plus n minus 1. Okay. Okay, let's assume this is n is equal to 2. 1, 2, 3. Actually, it's better if I write this. On this part, this is n is equal to 2. So I want this to be here. And then this entire thing d when d plus 0k. D plus d plus k. D plus k plus d plus 2k. How many times is this adding? Wait, hold on. The sum of this would be the first one plus the last one n over 2 times. Yeah. Let's say there are only these many. D plus 3k is 2d plus 3k. D plus k and then d plus 2k is 2d plus 3k. So n is equal to 2. But should just write it. The reason I'm writing it like this because I want this to be n is equal to 2 and then this is n is equal to 3. So this plus this. This plus this gives this. This plus this gives this. Let me flip it. K and then EFT and D plus K. This plus this will give this. This. Then k here, this plus this would give 4k. So n is equal 1, n is equal to 3, 4, 5, 6. So d is equal. So for this middle one, it's like for a particular term, it's d plus n minus 2k, n minus 2 for the sum of the terms, n minus 1 over 2. 1 is starting from here, right? So we start from here instead, which is why I'm doing n minus 1. So 6 minus 2 is 5, 1, 2, 3, 4, 5. N minus 2, first one, plus last one. 2d plus n minus 2k. This is the sum. So if n is equal to 1, 1 minus 1 is 0. If n is equal to 2, we have 2d plus 0k, which is just d. N is equal to 3. 2 over 2 is 1. 2d plus 1k, which matches this. If n is equal to 4, 4 minus 1 is 3, 3 over 2. And 3 minus 1. 3 minus 2 is 1k. 3 over 2, so that's 3d and then 3k. Yeah. N is equal to 5. 5 minus 1 is 4. So this is 2. 2d. So in total 4d. And 5. This is 3. So in total 6. Okay, this works. So for a particular term, the sum is like that. N minus 1d. This is how we find a particular term. Hope I'm right. But the thing is, what is d and what is d is the first term, right? D is like this. This minus this gives d. D and k are both included in this equation. Can we write this equation without needing the thing, without needing d or k? Okay, let me think about this. we would need the at least 3 terms to figure out T and K, right? So A1, A2, A3. D is A2 minus A1. So we can write A1 plus can write it like this. We can replace K with the terms. Assume A1 is 3. So we plug in 3 here. 7 minus 3 is 4. So the first difference is 4. We plug in 4 here. Fourteen minus 7 is 7. 7 minus 4 is 3. Plug in 3 over here. 3 over 2 n square. Wait. A1 is equal to 3. Example 4.3.6. Seven minus 3 is 4. And then K is 3. 3 over 2 n. Is this formula correct? And this has to be like that. Three times 3 is 9. And then 3. 4 minus 9 over 2. 8 over 2 minus 9 over 2 is half. Minus 9 over 2. 8 over 2 minus 9 over 2 is minus 1 over 2. And then plus 3 over 2 n square. How do you prove this? How do you prove that The sequence that is delta 2 constant has a formula, has a degree 2 polynomial. Find a closed formula. Okay, never mind. Solving symmetries of equations with technology. The point of polynomial fitting is that if we can be sure that a sequence has a polynomial as its closed formula, then we can find that formula. Hold on, going back up, I want to solve this question. Find a closed formula for the number of squares on a n by n chessboard. So we start with 1, 4.3.7. Yeah. So 1, and then 1 plus 4 is 5. 1 plus 4 plus 9. So it's 1 square. So 1 big square and then 4 smaller squares. 1 big square and then 4 2 by 2 square and then 9 smaller square. 1 big square. So 1 big square and then 4 3 by 3 square. 9 2 by 2 square. Let me think about how to do this. 1 4 9 16 25. Okay. The big square only appears once. Going one unit smaller, we can shift the square in 2 by 2 spaces, right? So we have one big square. This is only the big square over here, 1. And then if we make it 1 unit smaller, we can move the square around in a 2 by 2 space. So 1 over here, 1. So 1, 2, and then 1, 2. So it's like a 2 by 2 space. And then we go 1 unit smaller. Now we can shift the square in a 3 by 3 space. So 1, 2, 3, then 1, 2, 3. So there will be total 9 of them. 1, 2, 3, 1, 2, 3, and then 1, 2, 3. And if we shift it again, we now have a 4 by 4 space. So when we are counting this, it's like 1 in a 1 by 1 space, and then 4. So uh, you have 1 by 1 space, which can fit 1 square. You have 2 by 2 space, which has 4 square, 3 by 3 space, which has 9 square. So once, so 1 square plus, we then go 2 square plus, then we have a 3 by 3 space. Then we have a 4 by 4 space, 5 by 5 space. All the way till n square. K square plus k plus 1 square. So d is 2 square minus 1 square, which is 3. But this is not the sequence though. This is the sequence for finding n. So the formula is this. So we are trying to find a closed form formula for Sn for this. So, okay, let's try doing this. But the thing is, how do we know that it follows this formula? 3 square 9, 2 square 4, 4 plus 5, and then we have 2, 4 square 16, 3 square 9, 9, right? 3. Hold on a minute. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9, 7. Yeah, 7. I don't know why I typed 7 minus 5 is 2. But the thing I'm wondering is, why does the sum of square follow this formula? Hold on. I think I already derived it before. Sum of squares. First positive integers. Let's evaluate this. So if we evaluate this, we are left with let S be what we are trying to prove. We will call the equation below 1. S be what we. Oh, so this I square. So what we are trying to prove. 3s plus 3 plus n. Okay. So this we already know sum of the this follows an arithmetic series, which is this. Then let's expand this term. We have this, and then I think it's called telescoping, where the things cancel out. Simplifying, and then n plus 1 cube minus 1. We will call this equation 2. Combining 1 and 2, we have these two. Simplifying, this gives us our answer. Okay. So that's how I got that. k is equal to 2. Okay, anyways. 1 plus 3 n minus 1 plus n square minus 3 minus 2. There, these two cancel out. 1 plus 3 n minus 3 plus n square minus 3 n minus 1. Is this correct? 3 n square minus 3. So n square. No, this is correct. Why did I get n square minus 3? If k is 2, d is 3, a is 1. Is this equation wrong? So why didn't it work before? It's a delta 3 constant. It's not delta. Okay, this equation won't work then. One square, two square, three square. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. 25 minus 16 is 9. Seven, 9, 2. No, I think what I figured out was finding the term, not this. I found the term. Yeah. The term is found like this, not the series. But shouldn't it just be n square? Why is it even? Oh no, let me see what's going on. Why did I get this wrong? Shouldn't it just give n square? So 1, 1 plus 3n minus 1 plus n minus 2 n minus 1. Okay. N square minus 3n. This is not 1. Plus 2 plus 2. Now it makes sense. I used the wrong formula. Need to find the series. The formula for the series is this, but how are we supposed to calculate it without that? I'm just supposed to assume that it's cubic. Okay, I think we are just supposed to assume that it's cubic. But won't we need to prove that it's cubic all the way? Like, how do we know that the series is cubic so far as we have calculated? Like, what if it stops being cubic at a certain point? Like, this over here would be the proof. This here is the proof that the sum of the square is this formula. But over here, we're just assuming that it's stays cubic, right? Like it stays delta 3 constant. What's after this? Technology. Oh, they're using Python and then it's just review. For a degree 2 polynomial, we need to find 3 coefficient. A system of 3 linear equations will be enough to find these 3 unknowns. In fact, A0 will be the constant term. We can really get away with just 2 equations and 2 unknowns, and this is not difficult to solve by hand. For higher degree polynomials, the number of equations is larger and solving by hand can be tedious. Luckily, it is easy for computers to solve these equations. Below, we demonstrate how to use the free computer algebra system SageMath. Now, just skip this part. Does this work now? Yeah, it does. Match each sequence on the left with the type of the closed formula it might have. Okay, let's see. Quadratic, cubic, exponential, linear. 3 plus 1, 4, plus 3, 7, plus 4, 11, plus 7 is 18. So plus 1, plus 3, plus 4, plus 6, plus 11. It may be exponential. 3, 4, 7, 13, 23. 3 plus 1. Wait, hold on. 4 minus 3 is 1. 7 minus 4 is 3. 11 minus 7 is 4. 18 minus 11 is 6. Okay. 4 minus 3 is 1. 7 minus 4 is 3. 13 minus 7 is 6. 23 minus 13 is 10. 3 plus 2. Okay, what about this one? 3, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This is linear. 3, 5, 8, 12, 17. 5. So 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 4 is 12. 12 plus 5 is 17. Quadratic. Now the question is between cubic and an exponential. 3 plus 1 is 4. 4 plus 1. 3 is 7. 7 plus 1, 2, 3, 4 is 13. So 1. So 1, 3, 1, 3, 6, 10. So 2, 3, 4. Okay. This is cubic. Wait a minute. 2, 3, 4. Quadratic. Cubic. Aren't both of them quadratic? 3, 5, 8, 12, 17. 3, 5, 8, 12, 17. 3 minus 5 is 2. 3, 4. Then 12 plus 5 is 17. This is quadratic. Yeah, actually. Yes. 1, 1, 1, 1, 1. This is going 2 layers deep. This is going 3 layers deep. The actual sum is above this. Yeah. Then this is exponential. Yeah, correct. I will end the stream here. It took longer than expected. And then next stream, I'll start studying the exponential stuff. Anyways, I'll see you guys next time then. Bye.